to introduce Aaron Brown from Northwestern University. He will talk about stationary measures for random dynamical systems. Thank you.
Okay. So this is working? So yeah, so it's a pleasure to be in Rio and be at IMPA. This is my third trip here. And yeah, nice to see some old friends and also meet some new young people. So my course is about stationary measures for random dynamical systems. So I'll define stationary measures and I'll define random dynamical systems in about 25 minutes. But I want to start by giving some sort of context for the kinds of results that I want to talk about. So I want to take about maybe 20, 25 minutes to talk about sort of ternary or three-adic fractals. And Balazs's course is about fractals and why they're nice, and maybe for 20 minutes I'm going to tell you why fractals are really bad and I don't like them, but we'll see. So the space I'm going to work on is the circle, which I think of additively, so R mod Z. The dynamics I'm going to take is the tripling map. So f from S1 to itself. F of x is 3x mod 1. Oops, maybe I can't fit it. Mod 1. OK, so I think probably we all know this. We've studied this a lot. And given x in the circle, its orbit is maybe fancy O of x is just its orbit under the dynamics. So x, f of x, f squared of x, etc. And maybe my question is, what kinds of orbits exist? Orbits occur. OK. Or what kind of behavior occurs for orbits? So we can describe orbits topologically, so topological. And if I take a rational point, so if Q, maybe if x is in Q, then the orbit of x is going to be finite, and it's going to be closed, because it's a finite set. In particular, x is going to be pre-periodic. So if you take x equals 1/2, maybe let's see, 1/12. 1/12 maps to what? 1/4, which then maps to 3/4, which then maps to 1/4, which maps to 3/4, etc. So here's a pre-periodic point. And also, there exists x in the circle with the orbit of x dense in the circle, so I can look at the orbit closure, and that's everything. In fact, there exists lots of points with dense orbits. I think we all know this. We've taken some sort of basic course in dynamical systems. And then there's some sort of statistical or some sort of measure theoretic version. And so here, let me observe that if I take fancy m to be the Lebesgue measure on S1, this is f invariant and f ergodic. I'm assuming we know what these things mean. And you've done the proof, and you can do the proof by Fourier analysis here. And so the ergodic theorem, the pointwise, ergodic theorem says that almost every point its orbit equidistributes. So for m, almost every x, fancy O of x equidistributes, and I'll write out what it means in terms of the ergodic theorem, equidistributes. So what does it mean to equidistribute? It means that I take the delta mass along the orbit. So I take the first, okay, so here's the kth iterate of x. I put a delta mass there. I sum from k equals 0 to n minus 1, and I average, so I divide by n. So this is the first n iterates of the orbit. You put delta mass on there, and this converges in the weak star topology to M. So this orbit really in a very statistical way starts looking like this measure M. Okay, so I think I haven't said anything that nobody in the room knows, or doesn't know, or whatever. But is there any other behavior? And of course there are, because there's lots of fractal objects inside of here. So for example, let's let lambda, maybe fancy C. This is the 1/3 Cantor set. And I'll leave some space here. So here's my circle with ends identified. And if I throw out the middle third, and then I throw out the middle ninths, so this is what, 7/9 and 8/9. And of course, we all know how to build the Cantor middle third set. This is F invariant. And I can also put a special measure on here. So mu, fancy C, this will be the 1/2 Bernoulli measure on fancy C. And so what does that mean? This measure is going to give charge 1/2 to the left third interval, and it's going to give charge 1/2 to the right third interval. And then these four intervals are each going to get charge 1/4, 1/4, 1/4. And you know how to build the Cantor set, and you can build a probability measure and a set from this. And this set, this Cantor middle third set, is F invariant, but it's really somehow indecomposable, and so it's topologically mixing. And this measure is also F invariant, and it's ergodic. And so we have some really nice orbits over here. We have finite orbits that eventually close up, and we have dense orbits, and we have points whose orbit equidistributes. But then over here we have some strange objects. And so for these strange objects, what else? What do I want to say? There exists X in this Cantor 1/3 set whose orbit is dense in the Cantor 1/3 set. So there are points whose orbit, or whose orbit closure, is some sort of exotic object. And there exist points X in here that rather than equidistributing to a finite measure or equidistributing to Lebesgue measure, they equidistribute to one of these strange fractal measures that equidistributes. Okay, maybe I should give up on the middle line. Equidistributes to this Bernoulli measure. And this set, I don't have to define Hausdorff dimension because Balázs did that for us. The dimension of the Cantor set is the same as the dimension of this Bernoulli measure. And this is log 2 over log 3. And log 2 over log 3 is not an integer, and so this is some sort of fractal set because that's fractal dimension. And now you say, well, maybe you just have periodic points, or you have orbits that are dense, and then maybe you have some fractal sets. And so either you're dense in a whole space or you're dense in a fractal set, and maybe fractal sets are nice, but you have lots and lots of fractals. So there are lots of fractal sets. So for every 0 less than alpha less than 1, there exists some F invariant topologically mixing lambda. So some closed invariant, so all my sets lambda, they're always closed. Maybe I'll put that here. Closed. And there also exists some F invariant ergodic mu. Maybe mu is supported. So with the support of mu equals lambda. So topologically mixing means that somehow it's not decomposable from a dynamical point of view. Ergodic also means it's not decomposable from a dynamical point of view. And with the Hausdorff dimension of lambda is the Hausdorff dimension of mu is equal to alpha. So you can find invariant sets of any intermediate Hausdorff dimension that you want. And you can find measures. The measure will always somehow be the measure of maximal entropy on this set, at least the construction I know. So you have lots and lots of fractals in here. And as a consequence of having lots of fractals is that you have lots of bad orbits. So just some example of bad orbit behavior. A topological, maybe topologically bad, meaning that somehow the orbit doesn't look like just a single nice object. So there exists X such that maybe if you take the non-wandering set of the orbit closure of X, which maybe I think it's called the omega limit set of X in this case, this is going to consist of two different fractal sets, a disjoint union of lambda 1 and lambda 2, where the dimension of lambda 1 is different from the dimension of lambda 2. So you can find points whose orbit is the orbit closure is basically two different fractals that have very different dimensions, and there might be some countable transitions between these things along the orbit, but if you take the non-wandering set, you ignore the countable transitions. And there also exists X such that the orbit of X does not equidistribute. Okay, I really need to give myself more room. Equidistribute with respect to any F invariant probability measure. And that's just life. Because you have so many fractal things inside of this dynamical system, you can spend 10 years shadowing one measure, then you spend 100 years shadowing a different measure, then you spend 1,000 years shadowing even a third measure. And there are just points whose orbit doesn't statistically look like any invariant measure. Okay, so maybe why is this bad? Or why is it good? I don't know. Maybe it's good because you think these are interesting, but it's bad from some perspective. So maybe here's a philosophy. So if you pretend that you're a number theorist and you like questions about numbers, the philosophy is that sort of a question in number theory, has a dual life in properties of the orbit of either specific points or all points. So this is a common principle. If you have a question number theory, you find some dynamical system, and you want to either understand a specific orbit or you want to understand every single orbit. And just some examples of this, and orbits, but what do I mean by orbits here? We've started with one example, which is a simple dynamical system, but orbits of some group action. So what are some examples of this philosophy? So if I want to say that X is normal base 3, that's exactly the same as saying the orbit X equidistributes to the Lebesgue measure. And we know that almost every point equidistributes, so we know almost every number is normal base 3. But if I give you a specific number, how do you check whether it is normal base 3? Birkhoff doesn't tell you which points actually equidistribute, which points satisfy the Birkhoff-Ergodic theorem, just says that almost everyone does. If I hand you a specific number, how on earth would you actually check that it satisfies the Birkhoff-Ergodic theorem or that it's normal base 3? And if you want to be fancier, so there's a lot of things you can put here. I'll just give 2. Oppenheim conjecture. Which is now Margulis's theorem. Is the same thing as studying not a single, so when I say equidistributes here, of course I mean for x goes to 3x mod 1. Here I need to study a different dynamical system. I need to study every SO2, 1 orbit on some space on SL3R mod SL3Z is either closed or dense. Okay, so I'm not going to talk about Oppenheim at all, but just to show you a flavor of why you might want to be able to either test a specific point and understand its orbit, or whether you'd want to see the behavior of every single orbit. Here's two examples where you start with a number theory question and it really translates to properties of a specific orbit or properties of every single orbit. So, okay, the first 20 minutes was to try to convince you that somehow having fractal objects, in particular having lots and lots of fractal objects, makes your dynamics messy and hard to analyze. So then let me go to bullet point 2, which is something about large group actions. And I'll try to get through 2 stories of this today. So the first story is, again, let's take X to be the circle. Let's take F from the circle to itself. F of X is 3X mod 1. But now I want to build another map, which is G. And G of X is 2X mod 1. And because we're on the circle, linear maps on the circle are just multiplication by numbers, and they commute. And so remark is that G composed with F is F composed with G. And so if you look at the group generated by these things, F and G, they generate a copy of n squared. There's also no relation, so G to a power is never F to a power. So they generate a copy of a higher rank abelian semigroup. So this is a higher rank abelian semigroup. And again, there's sort of a principle here. Which is if I take fractal objects, but I could take two kinds of fractal objects. I could take F invariant, and I could take G invariant. So there's a bit of a tree here, and then it reconverges. But if I take an F invariant object, it is somehow supposed to be 3-adic. And if I take a G invariant object, it's supposed to be 2-adic, or ternary and binary. And somehow the set of 2-adic things intersected with the 3-adic things is supposed to be somehow trivial. And there are various theorems along this line. Let me tell you two of my favorite. So the first theorem along this line is due to Furstenberg. And it says the following. Let lambda, subset of the circle, be closed and invariant under both, and F and G invariant. So let it be a closed invariant set, but closed for both the dynamical systems. Then either lambda is a finite set, and because these are endomorphisms of a compact abelian group, this forces lambda to just be inside of the rationals. Or it's everything. So somehow having this extra symmetry, adding F and G, the fact that 2 and 3 are co-prime, the joint invariant objects, somehow there's no fractal objects that are invariant under them. So finite sets have Hausdorff dimension 0. This has the full space, which has Hausdorff dimension 1. And this is the story for closed invariant sets. There's a story for measures as well. So the best result in this direction is due to Rudolph, but it sort of builds on work of Amy Johnson. And it's the analogous thing for measures. So let's let mu be a, and here I'll say ergodic F and G invariant Borel probability measure. If I forget to write down probability, all my measures are always probability measures. So again, there's a dichotomy, then either. And what you'd really like to say is that the measure has to be finitely supported. We don't quite know how to show this, but we can say something in terms of it being non-fractal, which is that the Hausdorff dimension of mu has to be 0, or the entropy has to be 0 for any element in this semigroup, or mu is the Lebesgue measure on S1. And so again, Furstenberg and Rudolph, they tell us that there's no fractal jointly invariant objects. There's no intermediate objects of intermediate Hausdorff dimension that are invariant under both F and G. Okay, and there was supposed to be a letter here. Large group actions, yes, A for abelian semigroups. Okay, so pause. Are there questions at this point? Just with sort of a motivation and setting some stage. I don't want to talk about abelian groups. I want to talk about things like the free group. So I'll make a transition right now. Okay, so bullet point B is somehow something about large actions of, well, essentially they're going to be more or less free groups in the end. Large actions of large groups. So there's a few things I don't like about the circle. First of all, these endomorphisms are not invertible. So I want invertible dynamics. I want group actions. And also, all the endomorphisms, they commute. And I really want some things that don't commute here. So let's take our space to be a d-dimensional torus. Eventually, d is going to be 2. So if you want, d can just be 2. So our d mod z d, and so d here is at least 2. And now I'm going to pick A1 through AK. These are going to be d by d matrices. They're going to be integer matrices of determinant 1. So SL dz. And I view SL dz in a couple of funny ways. I'm going to view it inside of SL dr. But I'm also going to view SL dz as the automorphism group of the torus. And eventually, I want to think of the automorphism group of the torus as sitting inside of the diffeomorphism group of the torus. So I won't use different notation for when I think of this as a matrix or when I think of it as an automorphism of the torus or a diffeomorphism of the torus. Am I missing anything? No. Okay, so let gamma be the group generated by A1 up through AK. And group or semi-group, it doesn't really matter for what we do here. And somehow I want this to be either a big group or what I really want is that's a big action in some sense. So what I want to do is I want to suppose or assume that gamma, some notion of it being big or being large is that it is Zariski dense in SL dr. And I'll even box this in. And I'll admit that I don't know very much algebraic geometry, so I don't have a good sense about what Zariski dense means. So part of this whole story that I want to tell you this week is about how do you think about Zariski density dynamically, and how do you replace Zariski density with some more dynamical condition that maybe you can check in some group actions. But I want to ask some similar questions. So questions, what are the gamma invariant sets and there are some obvious gamma invariant sets. Maybe I'll say sets lambda, question mark. So there are some obvious ones. You could take lambda is the whole torus, or you could take lambda sitting inside of the rationals again. And so because the entries here are integers, if you take any subset of the rationals, okay, let's take it finite. Okay, sorry. There are finite invariant sets. Lambda, finite, and a finite invariant set is going to have to sit inside of the rationals. And if you take a subset of the rationals, a finite subset of the rationals, its orbit will also be finite. So here are some finite invariant sets. And what are the gamma invariant probability measures? And again, there are some examples. There's the Lebesgue measure or the Haar measure. on the D torus. And there are finitely supported measures, so just finitely many delta masses sitting on some finite invariant sets. And the question is this everything? So really the question is, these are some obvious invariant sets or invariant measures, and are there others? And if you know a little bit about analytic group theory, you might know that I'm asking maybe the wrong question. Because this is a bad question to be asking. So remark is that gamma being Zariski dense is going to force gamma to be non-immutable. Non-amenable. Whatever that means. So what does non-amenable mean? It means that there are continuous actions on some space that have no invariant measures. So this means that gamma acts in a C0 way on some compact metric space with no gamma invariant probability measure.
Sorry.
Yes?
What is the Zariski dense?
What is Zariski dense? Okay, well, go take an algebraic geometry class, so then you learn what Zariski dense means. It means that if you try to fill it out with polynomials, finitely many polynomials, you get the whole space. But I don't really care what it means. I'm going to tell you some dynamical consequences and how I think about it from a dynamical point of view. So I'm going to give a few exercises. So here's exercise 1. Exercise. Let A and B be in SL2Z. So 2 by 2 integer matrices with a determinant 1. I'm going to assume that they're hyperbolic. And that they don't commute. So A composed with B is different from B composed with A. So this means that their eigendirections are going to point in different directions, and that's really all you need. So then we let gamma be the group generated by A and B, and it acts on the torus with an invariant measure because it acts on the torus with the invariant Haar measure. So I want to let it act on something else. I'm going to let it act on the circle by Mobius transformations. And maybe if I'm, here I'm thinking of the circle as the boundary of the hyperbolic plane. And so this action show there does not exist any gamma invariant probability measure. And the hint is to use that you have hyperbolicity, so you have positive and negative eigenvalues, and the fact that they don't commute means that the eigendirections point in different directions. And if you know what ping pong is, you can play ping pong, and you can just use that to show that there's no gamma invariant probability measure. So somehow this is a strange question to be asking, because the kind of groups I'm looking at have lots of actions that don't have invariant probability measures. And when you start doing these kinds of stories, maybe you only care about the topological question, so you only care about what are the closed invariant sets or what are the orbit closures. But often a way to probe the invariant sets is to take a closed invariant set and put a probability measure on there. But maybe you have some exotic closed invariant sets that emit no invariant probability measure. And so then you need another tool. And so now I can finally introduce the first two words of my title, about what are stationary measures. So stationary measures are how we overcome the fact that these kinds of groups probably don't have invariant measures, but they'll have stationary measures, and maybe we can study those. Okay, so C is just a primer. Yeah, primer on random dynamics. Okay, so here X is compact metric. And mu is a probability on, not on X, but on the homeomorphism group of X. And this I view as a dynamical system. This induces the ID random walk on X. And so how do I view this as a dynamical system? I can think of how it acts on points. So if I take a point X, it's going to go to f of X sort of with probability mu of f. So a point is going to go to some other point, but you don't exactly know where it's going to go. You only know where it's going to go with some probability. And this is maybe not the right way to look at it. You can also look at the action on point masses on atoms. So delta of X is going to go to what I'll call mu convolved with delta of X. And this is just the integral of f star of delta of X, where I integrate with respect to mu of f. And this is, of course, just the integral of delta at f of X. So you take a delta mass, and then you're going to send it to a cloud of where all the possible places X could go under this IID random walk. And really the right way to think about it is this is a dynamical system on probability densities, on probability measures. So if I have any density on my space, it's going to go to what I call mu convolved with nu. And what is that? I push forward under a mystery dynamics F, my measure nu. I integrate over all possible Fs. And so maybe the picture is I start with, here's my space X. Instead of looking at a point, maybe I'll look at a delta mass at that point. And now maybe my mu, the support of mu, maybe it sits on 3 different maps, F1, F2, F3. And so if I apply my dynamics once, that one point mass is going to go to maybe 3 different point masses. And they might have different weights. I'm just going to draw them as dots. So this is F1 of X, and this is F2 of X, and this is F3 of X. And what I've drawn over here is mu convolved with the delta mass at X. But then if I apply my dynamics again, probably I expect to see 9 points unless there's some overlaps. So, okay, I'm not going to label them all, but here's 9 points. And this I might call mu convolved with delta X. And I might shorthand that to mu. Maybe I'll say mu raised to the second power convolved with delta X. So I start with a 1 point mass, it goes to 3 points with some density, some weights. I'm not drawing the weights, and then it goes to 9 points, and then, after I do this 3 times, then I really probably get 27 points. And so a point mass is going to go to something that really is some probably cloud of points that really is starting to look like a continuous measure after I do this a bunch of times. And here, every time I act, I'm acting identically distributed with respect to mu, and I'm acting independently, so that's what IID is. It's that this is a identically distributed independent random walk. Okay, so actually, I told you what the kind of random dynamical systems I want to study. They're IID random walks given by some measure on the group of homeomorphisms of a space. And now, what is a stationary measure? So first, let's let gamma sub mu be the group of homeomorphisms generated by the support of mu. So definition, a probability nu on X is gamma mu invariant if what? If f star of nu is equal to nu for all, let's see, for mu almost every f. And you can check that this is the same thing as saying for all f in gamma and gamma mu. So these are two equivalent definitions, but they're the same. So this is a very strong condition. You want to actually, the measure is invariant on the nose under every single element of the group, and these might fail to exist. And so then we would say it's mu stationary if this happens, but if this happens on average. If f star nu is equal to nu, but here I want to average, so okay, so let me put this in. Put the averaging is equal to nu. And so here's, I'll give you a subset of the exercises I plan to put here. Exercises is, well, before I put the exercise, let me put one observation, which is that the mu stationary measures certainly includes the gamma mu invariant measures. Right, if you're invariant, you're also stationary. This might be equal to the empty set. And so one question is, do you have any invariant measures? So when is this non-equal? And another question is, when are these things the same? When is every stationary measure mysteriously actually invariant for the group it generates? Okay, so here's a couple exercises. One is that gamma invariant measures might not exist, but mu stationary probabilities always exist. That's the Krylov-Bogubliobov theorem. You have to reformulate it. Was there another exercise I wanted? Another exercise is that if nu is finitely supported and it's mu stationary, then nu is actually gamma mu invariant. So here's an example of a case where stationary measures automatically become invariant under the whole group, and it's if it's just finitely many point masses. I guess it's true what I said, but here let me put ergodic, just to make it easier. And 3 is the Choquet-Denny theorem. If gamma mu is abelian, or virtually nilpotent, but I'll just say abelian, then the mu stationary is actually equal to the gamma mu invariant. So every stationary measure somehow is invariant when you have when the group is not too complicated, say if it's virtually abelian or virtually nilpotent. Okay, so this was an abstract primer on random dynamics where our space is a compact metric. Our dynamics is IID homeomorphisms. We want to study some statistical properties. There might not be any invariant measure, so we relax what invariant means to introduce stationarity. And now let's go back to the setting that I introduced in bullet point B, which is affine random walks. So now I'm going to take mu is finitely supported on SL dz. You can take d to be 2 if you like. Gamma mu, this is the group of integer matrices generated by the support of mu. And so this is some finitely generated subgroup of SLDZ, and you can view it inside of SLDR. And you can also view it inside of the automorphisms of the D torus. And again, suppose gamma mu is Zariski dense in SLDR. And again, I don't want to know what Zariski dense means. I want to replace it with some sort of dynamical criterion. But this is a starting point to end with, I think, a beautiful theorem from the last decade. So this is the theorem of Benoit and Quet. And I don't know exactly when am I supposed to stop? 5 minutes, okay. So then I can say all the bullet points. So these are the hypotheses. Finite random walk by automorphisms of the torus. We're going to assume something that makes the group big and the action somehow big, which is this Zariski density. So one is rigidity of stationary measures. Every mu stationary, and here I'll say ergodic, mu stationary probability, nu is either finitely supported or it's the Lebesgue measure on the ambient space. So this is a lot of work to prove this. The Lebesgue measure is actually invariant under the entire SLDZ. And I gave you the exercise to say that if you have a finitely supported stationary measure, it's also invariant. And so as a consequence of this, you get what is called stiffness, that this action is somehow special and that every potentially stationary measure, which might not be invariant, is actually invariant. So every mu stationary probability is gamma mu invariant. It's actually on the nose invariant by the whole group. And I can't fit the other two bullet points there, so I'm going to come way over to the left. Once you've classified all the stationary measures, then you can go back to the topological problem, and you can show that every orbit is either finite or it's dense. So there's no topological fractal things in there, and there's no objects that sort of shadow a finite thing for some time and then jump to another finite thing and then eventually become dense. You're either finite on the nose or you're dense. And 4, if x is not rational, maybe q to the d, mod z to the d. So if you're rational, you're going to have a finite orbit. If you're not rational, you're going to have a dense orbit, but you're actually going to have a statistically dense orbit. Then the orbit of x equidistributes to the Lebesgue measure on TD. And so by having this big group acting, we don't have any of these fractal objects appearing, and we also don't have any of this transient behavior of things that are shadowing different kinds of behavior. Either you are finite because you started off rational and you stay rational, and so you have finite orbit, or you're dense, and when you're dense, you actually equidistribute following Birkhoff. And maybe Alejandro gave me 2 more minutes, so I'll write down what it means to equidistribute in the case of random dynamics or stationary measures. So you start with the delta mass at x, and now you're going to convolve it under the dynamics, but the dynamics is this random dynamics. So you take mu to the k convolved with delta x, and you sum from k equals 1 to n, from 0 to n minus 1, and you divide by n. And so here you're taking all IID words of length k, distributed IID with respect to mu. So you're taking all possible futures of x under words of length k. And this is going to converge to the Lebesgue measure on the torus and in the weak topology. OK, so I'll put the chalk down. So what is the goal for the next 3 days? I don't really care about automorphisms of the torus. I don't care about its risky density. I don't care about algebraic geometry. I don't even really care about number theory. So what do I want to do to these kinds of theorems? Is I want to take them, and instead of looking at actions on the torus by nice algebraic things, I want to perturb these and now look at actions by diffeomorphisms. And I want to do nonlinear dynamics, but inspired by this kind of theorem. And I want to see how far we can get with nonlinear dynamics in this setting. And I want to replace the risky density with something that's more meaningful to me, some sort of dynamical criterion. And so that's the goal for the next 3 days.